Okay, so now this should work. Okay. So this is lecture 19, and this is optimization. Okay, excellent. This is the 2nd of March, 2021. Oh, I'll tell you. I thought everything would be okay, and I tested it this morning. I had rebooted the machine. Windows Update had done something, and then it had knocked out my setting on my microphone. So hopefully everything is okay. Okay, so yes, we did a quiz today. And hopefully everyone did okay. I think it looked fine from what the statistics I was seeing as it was coming in. So that's good. And we also have a new assignment that's posted. It's posted on Moodle. But right, so we're going to talk about optimization. We had done some, we have all the tools, we have some derivatives. Now let's start to build some stuff with it. We're going to use some applications for it. So, and what we're going to talk about today is global minimums and global maximums. Okay, and thank you everyone for hanging tight for that. I see people are joining back. Welcome. Windows 10. And don't worry, for those that have said, oh, I should be using a Mac. Yes, I have definitely crashed Macs before. Give me a machine and I will somehow Okay, so what I'm talking about here is we have an intuitive idea of what a global minimum or a global maximum is. For instance, when we think about the temperature, say in the morning it's quite cold, we'll start at time 0 and we'll end at the 24th hour, just before it. So again, it's kind of cold in the kind of early hours. It gets warmer, and then back down. Something like that, maybe. So again, there's kind of a clear maximum here. So right around here, maybe around the midday, a little bit later, we actually get a peak, and that is what we'll call this is a global maximum. And then we can look for where it's the lowest point, which is the global minimum, and we find it right at this endpoint here. So right here, we have is the global people are asking, again, we said that I hope to have them back by Thursday is when I expect to get the test 1 results back. I'm just a little bit slower because I'm marking it on paper. I have to scan it. It just takes more time. And so again, the idea here is that when we're thinking about this example of working on like the global temperature for the day, we're working on a specific kind of interval. We're working on this closed interval from 0 to the maximum, the 24th hour here. So it's kind of closed. So we kind of have that idea that we're working on an interval. So let's add a little bit of some formalism. So the formal definition so we let f be a function defined on an interval. So I hope I got Seller's question. I think I covered everyone else. Okay. So we're going to have some function. It's going to be defined on an interval I. Then if we let m be some real number such that the function at x is less than or equal to m, so it's kind of like the biggest value that it'll be for all x in the interval, and also that value or that function at some point x naught has to actually equal m. So for some x naught in I. So if it satisfies these two conditions, then we call m is the global max of that function. And then we also specifically make it a little bit more detailed by saying it's on the interval. So that's for the global maximum value. And similarly, if m is also a real value such that for all x in that interval, that so all the possible values in here has to be less than this value. So again, all the other values here are smaller. So again, or sorry, yeah, there we go. That all these are bigger than m. And then there is some point in that function that actually equals m. And that is what we'll call the global minimum. On that interval. So this is an observation that is actually put into a theorem, that you can have a global minimum and a global maximum on a closed interval. And so they call that in the textbook the extreme value theorem. So that is an actual theorem that they use. So it's the extreme value theorem. And what they say is that let f be continuous. So f is continuous. Okay, so that's the first condition. And the second one is that I is, so it's on an interval, so on I, and I is a closed interval. So here's kind of like, I was marking some logic. So if you have f is continuous on an interval, and the second condition is that I is closed, then f has a global max and a global min. On I. Okay. So we can start to use that theorem to actually do here's an example. We could use, let's try this. Here's an example, and it's, find the global minimum and maximum of, we're going to use this function 1 over 1 plus x squared on the closed interval 2, minus 2, 2. Now the idea here is we have a closed interval, and so that means that it has to ascertain a global max and a global minimum. This is also, well, is it continuous on the domain? That's something we should be careful about. The only time that this could be not defined is when that is equal to 0, and I get minus 1. And again, that's not in the reals. So no, it's fine. So we're completely defined on that domain. What I can tell you though is I can do a little quick sketch. Now you might not know how to draw this, but again, we're just to give you the intuition of what we're going to do. So something like that. So the idea is, I know roughly that it's going to be at 0. That's kind of where the maximum is. So how do we find where it's the maximum? Well, what we can do is using derivatives. For instance, like here, if I took the derivative here, this is the slope, here's the slope, and here's the slope, and same thing here. So I can draw little slopes like this. And so what you notice here is that when you're looking at the little slopes or the little tangents I've drawn here, the point that we're interested in is where the slope of the tangent is 0. So, basically we're interested where it equals 0. So those are the critical points, right? We're interested where that's equal to 0. So since that means that I need the critical values, that means I need to find the first derivative. So we need to take that derivative. Okay, so we can use the you could use the quotient rule. So if you did the quotient rule like that, you could do, it's the derivative of the top, which is 0, times the bottom, minus the top function, times the derivative of the bottom, 2x here, all over 1 plus x squared, and this needs to be squared. And that equals, so that cancels out because we all have 0. And then I'm left with 2x over 1 plus x squared. And then I'm going to set that to 0. So setting that to 0, get minus x over like that. I can bring that over to the right hand side, so 0 times that leaves me with 0 on the left hand side there, and I'm left with x equals 0, which is what I expected because that's kind of what my intuition was. Right, so why was I humming and hawing about this part over on this? Because again, we could have also written f at x equals 1 plus x squared to the minus 1, and then we could take the derivative of that using the chain rule so that the minus 1 comes down in front. I leave the inside alone, this becomes minus 2, and then I take the derivative of the inside, which is 2x. So that leaves me with 2x over 1 plus x squared, like that. Anyways, we have our critical point, and what we have is the extreme value theorem here that says that it's on these closed values. Now notice here, like we could build a little table. Just like that. And I have one value, so I have 0. So if I plug in that value, that's 1 over 1 plus 0 squared, which gives me 1. But I made this a little bit longer. The reason for that is, just remember here, I'm on my closed interval. And just like here, I actually had a case where the global minimum or global maximum or whatever ended up being on the endpoint. So what we also need to do is we also need to test for the endpoints. Now we are given an endpoints here. We're given minus 2, and we're also given 2 here as well. So I get 1 over 1 plus minus 2 squared, which equals 1 over 5. So I got 1, 0, comma 1, minus 2, comma 1/5. And Joe, or Mr. MAE, is making sure I have my negatives right. Please, please catch if I do. That would be, that's a positive. So again, that becomes 1/5. Everything look okay? Everyone's following along? I don't fall on either side of the debate when it comes to Mac or PC or Linux. I always seem to run into something. Yes, we run Linux at school. I've run Macs before. Run PCs. I will say since Windows 7 and Windows 7, that was a really stable operating system. So it only keeps getting better. So we finished this part off, and so all you have to do now is we look at where the bigger value is. So here, this is the interesting one. This is where we have, this is their global max. And interestingly enough, I got two minimum values. So here's my two minimums. You can have this, you notice that the value, you don't necessarily have unique, like only one global maximum or one global minimum. You know, for this, just note, again, it's for some value. When it says for some, it's meaning that it does not have to be, there has to be one, but there can actually be many. So again, for some. So for some value, not necessarily unique. So again, we've got our 2 points here that are global minimum, and I have a point here where it's my global maximum. Excellent. Okay, so maybe I should summarize that, because what we've done here is we found critical points, and we found that the critical points lie within the interval. We calculated where the critical points were, and then we calculated where the values at the endpoints. And then at the end, we picked the biggest and the smallest values, and those correspond to the maximum, the global maximum, and the global minimum, respectively. So that is what they call in the book the closed interval test. I might write it just a slightly different, but... So again, to find the global minimum or the maximum of some function f, and it has to be continuous on the closed interval. And for this to work, we also require that it be differentiable because we're finding the first derivative. So again, that's another condition that we wanted. So differentiable on the open one. And so I said we found, first of all, the critical points. So find the critical points. Then the second thing is we compute the values of f at the critical points and at f at A and f at B. So then we made that table. We got that table of values, and then you just read off from it. You just pick the largest value. So the global maximum value and the global minimum value of f will correspond to the largest and the smallest numbers, respectively. Found in step 2. Okay. So let's since we've kind of got our intuition for this. This is our test. This is some good stuff here. There's some tools. It's good here. I'll put a little line there. Okay. So again, we'll do that example. We'll have to find a global minimum and a global maximum, and we'll use this function here. We'll use x to the 3 minus 2x squared minus 4x plus 4. And we're going to use on the closed domain 0 to 3. So we have the recipe card up here. Because we're all using recipes now that we're stuck inside and we have to cook ourselves. Yes, I know how, Grubhub and there's this other delivery service, but again, you're talking to the same person who still didn't manage to get audio to work on the computer. So this is the recipe. So step 1, find the critical points of f. Right. So critical points, I have to find the derivative. Right? So critical points, that's where goes to 0. So finding the derivative. Oh, yeah, I'm not sure. Yeah, I think it would be, cooking is kind of therapeutic. So we found that. And what are we going to do next? Oh yeah, we need to solve for 0. So again, Maria's question would be like, can we leave it like that? Well, no, because we actually have to do something with it. We can actually factor this. We can actually factor this with, well, here's my x. I have my x minus 2 and my x, my 3x plus my 3x plus 2, so that when I do expand that out again, 3x squared plus minus 6x plus 2 gives me the 4x, or the minus 4x, and then the 4 times minus 4. Sorry, the 2 times minus 2 gives me the minus 4. And, setting that equal to 0 means that one of these terms has to be 0. So to do that, I have, say, 3x plus 2 equals 0 here, and I can bring the minus 2 over to the right-hand side. And so I got x equals minus 2/3, and on this one I have x minus 2 equals 0, x equals 2. So these are my two critical points. Now, the nice thing about this, okay, so let's go back to the recipe card. Find the critical points in A, B. Now, my A and my B here is 0 and 3. This one, x equals 2, is between 0 and 3, but this is clearly not. It's minus 2/3. It's not in that interval. So that is not admissible right now. So I don't care about this point. It's not in 0, 3. Okay, so I got that. So I have my critical value. Now I'm going to create a table. There we go. So I need to calculate the values at the critical points and at f and a and f and b. So I have 2, which is one of my critical points, and then I have 0 and 3. And so I can actually sub this in. I'll do the 0, don't worry, that's the easy one. So I have 0 cubed minus 2, that's 0, and this is 4. Oh, now I gotta actually do some arithmetic. For this one, I have 2 cubed is 8. And then I have minus, so 2 squared, that's 4, times 2 is 8. Then I have minus 4 times 2 is 8. Plus 4. Did I make a mistake? Come on, gotta check on my work here. 2 squared is 4 times 2 is 8. Then I have another minus 8 plus 4. That cancels, so I should have everyone else got minus 4. I'm just also waiting for Joey, because Joey's the one that catches me for my negatives. Yes? Okay, good. It is correct. Good, good. I got people now. There's people. I know people. I know lots of people now. The best. They catch my mistakes now. This is how we build business connections. So that's good. Mr. MAE has signed off on that. So if we really screw this up, I will blame him. Because when you're the boss, no one blames you. You can blame other people. Then we have 3 cubed. 3 cubed. 3 times 3 is it's 27. Then I have 3 squared, that's 9, which is 18. Then I have 3 times 4, which is 12, plus the 4. So that's 18, so that's 30. I'm getting 1. Hopefully I added that up right. Whoops. Oh, good. Good. I am. Excellent. So, excellent. Good, good, good. So yeah, now, oh yeah, the recipe. The global maximum value will correspond to the largest value. So that is here. This is the global max. And the smallest value, this will be the global min. Oh yeah, and then let's live a little dangerously by me somehow. So how could I screw up the live streaming? By switching over to the monitor. So let's try it. Why not? This is Google, and we have x3 minus x squared minus 4x plus 4. And it should give us a nice little graph. Beautiful graph. Beautiful, beautiful. All right. So notice here that the graph actually has like this glow, like there's a maximum here at around, let's say, just looking at the values around, you know, about minus 0.6. And as I switch over to the, but we're looking from 0 to 3. So if we're looking from 0 to 3, then I'm not looking over at this point here. I'm actually looking from 0 to over a little bit past there. So maybe I need to move over a little bit. Oh, yes, there we go. So we're working from 0 to 3. And of course, I didn't zoom out far enough. So around 3. So we can actually look around 3. Yeah, that looks to be big. But our minimum is around, which we had written down, was around 2. Yeah, which was minus 4. And we also see that the biggest value is either at the endpoint. So it's at 3. And it's definitely not 3 because it's around 1. And when we look at 0, it's 4. So it looks like we're doing it right. So again, it depends on our interval. We can actually pick what we're going to look at, and that will give us our global and our, yeah, exactly. Okay, so if we have that graph. So I did that graph, a little graph there. So that kind of gives us a little bit of a visual. Right, so you're probably going, great, I can find, everyone wants to make money. So everyone's like, oh, okay, so great, you show me how to find a big number, great. Yeah, but that doesn't really, like, again, it's the context or the interpretation that makes you the money. So what makes you the money is we want to maximize profit. And again, you can already see if something was like this, you had a curve like this, which is our profit, then we should be able to maximize it. We could find the maximum profit for this. So that is how we're going to make some money. This is a very, very relevant. It seems that every 30 years stuff comes back. So here is an example. We have the Rega company. Rega is out of the UK. And again, this is a totally made up curve. So Rega, if you're listening, please don't send a nasty email from the, so we have, this is their total profit from manufacturing. I have the suspicion that Rega is not going and combing through calculus tutorials or lectures. So I think they have other things to do. Like they have to sell they're selling X units of their planar 2 turntable. And it's given by, because again, turntables are becoming more fashionable again. It's somebody has to explain to me very slowly how a digital file that is engraved in vinyl, how that has some sort of warmth to it, that analog feel to it when it's from a digital source. But these are questions that keep me up at night, but we can definitely help Rega out by finding what the profit is. It's in dollars. No, because they're British. It's in pounds. how many units of the planar 2 must reg a cell produce to manufacture profits? No, not to manufacture, to maximize. Manufacturing profits would be bad, especially if it's somebody wrote, because they convert it to an analog format while transcribing it to vinyl, which supposedly someone with a certain EO can tell the difference. Okay. Yes. I mean, there are some people who do argue about going through a valve or a tube amp somehow makes it warmer, even if it is a digital source. But I digress. So we can, did you forget a 0? Should it be 200? No. Oh, you mean over on here? I'm going to say that if they're making 200,000 turntables, that's a lot. I mean, we could make it, but no, it's just 20,000. 20,000, and here is 200,000. Probably that 200,000 is like their initial cost or something like that to tool or something like that, you know, to set up the tooling for it. All right, so we can easily do this derivative. The 2 comes down, so that becomes 0.04, negative 0.04 x plus 300. Okay. So again, we use our recipe, which is we're going to find the critical points, and again, set that to 0. So then I'm left with 0.04x Good. I see at least there's some chat today, so that's good. There we go. So again, I can solve for this. Something embarrassing. 4 goes into 30 approximately 7 times 28, so I'm left with 2. Drop 0 gives me 4 times 5, which is, so that means there's 75, 1, 2, 3, 4, 7,500. So that's our critical value. Is at x equals 7,500. Yes, excellent. Yeah, there's sort of some of the people that in chat, I mean, they're pointing out basically it's an aesthetic, and our ears like to have something that's a little bit smoother than a little bit jagged. So there's some people who enjoy an analog signal, even though it may not be as accurate as what it really is in the real world. And sometimes it's not, they're not necessarily after something that is accurate. They want something that is pleasing. That sounds good. So again, it comes down to the philosophy of the listener. Do you want something that's accurate, that might not be as nice to hear, or do you want something that is nice to hear but not necessarily accurate? And we see that all the time with video or sound. Right, so we did that. Oh yeah, what was our recipe? We have to go back to that. Number 2. Compute the values at the critical points and at f at A and f at B. Okay. So we have our critical values. $7,500, and then I also have at 0 and 20,000. So I can tell you that's easy for me to do because 0, 0 gives me minus 200,000. The 7,500 is a little bit more difficult. 925,000. And again, this would be something, you know, if you needed a calculator, sure. Going back to the idea of philosophies, I mean, you'll probably have calculators later in your upper years as well, so you might as well get used to some of these numbers. But again, this little calculation is not important. We've got these numbers. You can use whatever method. If it takes you a little bit longer to do it by hand, okay. But there's our table, and now all we have to do is pick out what was, you know, what's the biggest one, and this is our global max, and our really terrible one is our global min right here. But what we're after to maximize well, let me see if everyone keeps asking me if it's 20,000. 0.02 20,000, and I want to square that times, then I have 300 times, add that, 200,000, subtract, okay, perfect. Everyone's asking me about the, no. So this is the value, this is the function here, this is the profit function, and that's 200,000. And this is the domain. So again, this is the x. This would be this is like, for here, the 200,000 is the number of people. And Mr. Kohar is the correct salutation, or the, I wish I had my PhD. So, yeah, it comes from the interval. Exactly. And this would be, for instance, so this is like our startup cost, but over here, the x being between 0 and 20,000, again, that would be, you know, that Rega can produce between 0 and 20,000 turntables, which would be just an enormous amount of tables to produce in a day. So they say that's the absolute max, or the most that they can do. So they look at the extreme points. Yeah. And Yep. So we have our global. Okay, perfect. So Maria's checked it. So if we lose money, we'll all ask Maria for a refund, and then. Okay, so this is it. This is what we'll use. So it's, well, the boss wants us to kind of write out a statement. So Rega must produce 7,500 turntables to get the maximum profit. Of $925,000. Actually, and no, we said it's pounds. Perfect. Okay. What else can we do? Now somebody might say, can we, this is the end of that question. Somebody will go, do we have to test the endpoints? Well, if you're using the, kind of our closed interval test, or what were we calling it? The closed interval test, yes. Yes. If you're using that closed interval test, and no, well, we could. It's quite possible. We could use something called this. And this is called the second derivative test. Now, in the second derivative test, it's very similar. What we do is we're going to compute f prime and f double prime. So we need the first and second derivative. So again, for this would require that the original function be twice differentiable. So f is twice differentiable on the interval, but we won't have to be worried about that. So again, twice differentiable means that I have I can take the second derivative, and then what I can do is I can find the critical points or all of the critical points and then the third one, so what we can do then is compute the second derivative at those critical points. C. And if C is less than 0, which means that it's concave down, then f has a local max. So again, that's concave down. So woo, like the sad face. It's negative, it's sad. So frowny face, and oops. So f is a local max at C. Now if it's positive, right, it's got a happy face, then f is a local minimum at C, and if you're a downer, if it's equal to 0, then the test is inconclusive. Inconclusive. Okay, so here's 4. So let's do this. Let's do an example of this. So if I have this function, I have x cubed minus 3x squared minus 24x plus 32. So using the second derivative test, what I'm going to have to do is do these three steps. So the first one, find the first derivative, which is nice because this is a polynomial. So something nice and easy. We are going to have to find the critical value, so we should clean this up just a touch. And I'm just factoring this polynomial, or this trinomial here. And that is fine. Then the next thing is we can take the derivative again. So I got 6x minus 6. I can factor out that 6 to leave me with x minus 1. And so when I set that derivative equal to 0, what ends up happening is that I get x equals minus 2, and I get x equals 4. I don't have an interval that I'm looking at the moment. So both of them are in for the moment. Here we go. Page 5. So I got this. So I calculated where it's equal to 0, and then I calculate at the second derivative at minus 2 and 4. So this is my step 3 that I'm using here. And so what that's giving me is that concavity at that point. So it should, let's go and substitute that in. So I got, sorry, totally blanked out. There we go. 6, and then minus 3 gives me minus 18. And that is less than 0. And so according to that, since it's less than 0, it means that f is a local max at C. And the other point that I have is the 4. So four minus 1, 6 times 3 is 18, which is positive. And then that means that it's a local minimum. And again, so the concavity is down, which means that there's a point at the top. And this is when I have the concavity when it's going up. And so that means that it has to have a minimum. So F is a local min at x equals 4. Okay, so we just use the second derivative test to kind of find that. So we found kind of the local minimum and the local maximum. But again, that doesn't answer the original question, which is, do we have to test the endpoints? Okay, we're going to get there. You don't have to, again, if you do a little bit of more analysis. So let's do an example where we just do a little bit of analysis more about it. Okay. So what I should recall, I don't think we actually did talk about this yet, but we can actually talk about average cost. Or what somebody could say is, I think of it as like, it's the, you could think of it as cost per unit. Because when they say the average cost, they usually write, average usually is denoted with a bar over top of the letter. And we have our cost function. So this is what we'll call the average. And what they do is it's the cost function per unit, so per x. So what are we going to do now? So this is kind of just a economics term, because what we're going to do is we're going to do an example where we're going to look at the average cost of a manufacturing good. So the daily average cost function, and this is in dollars per unit, of the Manfrotto company. They make tripods. If we start to get into a debate over tripods in this class, I'm very worried. So hopefully everyone does not have strong opinions over which tripods that they prefer to use. Although, after teaching a while, I am both surprised and not. So this is the average cost function that they have. And this is for the domain where x is greater than 0. They're not gonna, so sir, in a previous example, the one where you showed us the graph, would x equal 3 be considered a local max? Oh, sorry. I should go, with the miracle of technology. Oh, there we go. Going back to x, it's not considered a local max. And the reason for that is because it's not, it's not where basically the derivative is equal to 0. We kind of look, basically this is at this point right here, that's where the tangent should be equal to 0. And if I can, I can move it a little bit. And around here, again, that's where the tangent is equal to 0. I might not know where, I would say because of just the concavity has switched, that this is a local, that's a local maximum, and around, so the endpoints don't determine the locality. The endpoints, when you introduce, again, if I go back to my, just a second. Where did they go? Papers. Oh, we're only on, okay. Oh no, it's the extreme. Oh yeah, it's the extreme value theorem. So again, it's when you're on a closed interval, then you're guaranteed a global maximum and a global minimum. You're guaranteed it because you are now within a closed interval. So for instance, I could have a function that looks like this. I could have something like this. I could have something look like this and something like that, and then something like, I don't know, something weird like that. Let's put in a coordinate system. And sure, I can see that there's a max here. I can see a local minimum here. I see a local max here. I can see a local minimum here. I can see a local max, minimum, etc., etc. Now, for instance, I could have that. Here's a maximum, but then I could have something where the function, you know, this is just ever slightly above here, and this is asymptotic. It gets really, really close to that line, but it never touches it. So it never actually ascertains like its true maximum value because it goes off to infinity. It's getting really close. So, you know, in this case here, over the entire interval, over the entire real line, it doesn't ascertain or obtain a maximum value. It just goes on forever. Now, as soon as you look at a closed interval, so for instance, you look at here and you look at here, then you've boxed in that function. So you're stuck looking at here, and you're looking at all these values in between here. And so, if this had a minimum, this is going to be now the global minimum. And over here, I'd look here and I'd look at the endpoints, and this is where it obtains the maximum value there. And that is the maximum value. As soon as we have a closed interval, we're guaranteed both a minimum, a global minimum, and a global maximum. But that is not the case when we're working on an open interval. And so the localness, or a local minimum or a local maximum, is simply looking at the behavior around that point. Yes. So, right. So in the earlier example from 0 to 3, our global yes, but the other endpoint, yes, exactly. Yeah. So if we were looking back at the other example, so once we close the interval, we don't care about the locals. No. Generally, if you're working on a closed interval and you've got some sort of optimization problem, which we were looking at, say if we're trying to find the profit and we are working on a closed interval, then we're guaranteed to find a global optimum. So maybe you might keep that in the notes. But yeah, it's that as soon as we put that closed interval on it, that we're guaranteed it. Now, this is going to be interesting, and the reason for that is we are going to try to probably minimize that. And what we're going to do is we're going to look around that, and the idea behind that function is that we're going to be looking at something that's probably something that, if we just look at something like that or like this, there's a kind of a local minimum here, and we're only working on this domain. And what we're going to basically say is that if it keeps going concave up, that at this point here, that it will be a minimum. And if it keeps going upwards, then and that it keeps going on forever like that, that means that it's a global behavior. Then this in fact becomes from a local minimum to a global minimum, and that's what this is going to try to do. Local minimum and local maximums are relevant. Yeah, they are relevant, and you might see more of this when you get up into higher up classes. But I will have to kind of postpone that because that kind of requires a little bit more detail. But there is we do need to discuss the ideas of local and global, especially when we get into numerical methods where you start to look for it automatically using a computer, and what ends up happening is that the computer will find a local minimum or a local maximum, and it didn't search enough to find the global one. So if it doesn't do enough searching for it, it might just stick to a local optimum, and that's not good. So that, again, that kind of requires a little bit more more advanced math. But these are good questions. So X stands for the number of tripods. I hope I answered it well enough at the moment, but we can always come back to that. So what we're asked is we need to show that a production level of 500 units or 500 tripods per day results in a minimum average cost for the company. Okay, I think Casey means if your interval has a local minimum or maximum inside of it in addition to, yes, it's still, so the question is if your interval has a local minimum or a local maximum inside of it in addition to the global maximum, or is it considered a local minimum or max? Yeah, it's still considered a local. Yep. But in that case, we're just looking for the globals. Okay, so what's interesting about this? We see that the domain of the average cost function is not closed. right? It's open. And I'm using round brackets to emphasize that. So we can actually start to use the second derivative test. So we'll have to first compute the first and second the first and second derivative. So to do that, the 2 comes down, so I got 0.0002 x minus 0.08. The 40, that's a constant, so that's 0. And then I have a minus 2. Or sorry, I have a minus 1, so the minus comes down in front. So I got minus 500, sorry, minus 5,000 x to the minus 2. And you can check by subbing in. So show that a level of 500 tripods per day results in a minimum cost. So again, if I substitute in the 500, you can check that this does in fact give you 0. And the next that we need to do, we need to take the second derivative. So I'm left with 0.0002, and then I have plus. So that minus 2 comes down in front, so the plus, the minus and the minus becomes a plus. The 2 times 5,000 gives me 10,000, and then that's x to the minus 3. Which is awesome, because basically without me knowing anything at the moment, this is a positive number. I have 10,000 divided by x to the 3, and those x's are positive numbers. So I know that this is greater than 0 for all x greater than 0. So that's good, which means then that I know automatically that if I substitute in that value of 500, I know already that it's greater than 0. So by the second derivative test, first of all, I know that this is a critical value, and that critical value at the second derivative is positive. So from that, I know that the local minimum of C bar occurs at x equals 500. Furthermore, we know that it's greater than 0 for all x greater than 0, and that implies that C bar is concave up on x greater than 0. So we have a local minimum, and what I'm going to do now is I'm going to show that it is a global. So because this is concave up, and it keeps going up and up and up, this implies that the local minimum of C bar must be the global minimum of C bar. And since we've calculated it, since the boss wants these for Manfrotto, we'll calculate what the average cost is at 500. So you substitute in those values. And with the magic of technology, it works out that it's $35 per unit. So with the last remaining minute, or a couple of minutes, let's jump over to the screen. And what I'll do is I'll put in that value. So 0.0001 x squared minus 0.08x plus 40 plus 5,000 divided by x. And okay, there we go. So we're looking around, yes. So we're looking for a minimum. This is good. So, and this is what we kind of expected, that this function is concave up over the entire x greater than 0. So again, I'm looking for the minimum value, and you know, if we wanted to think of it graphically, what we're trying to do is we're looking for where that tangent is equal to 0. So again, the slope, we are looking for when it kind of gets really, really flat, and right about, well, we already calculated it, so it's around 500. It's right around there, which is 35, which is good. It's matching what our original calculations are. And yeah, from the left-hand side of it, it's concave up, and it's concave up to the right-hand side of it, which means then that since we're at the flat, we are now at a valley here. It's as low as it's going to go, and it's going to keep going concave up for the rest. So it goes up to infinity on the right-hand side, keeps going up, and it keeps going up to the left-hand side up to to 0. And so yeah, basically using the second derivative test, we were able to show that while we had a local minimum at 500, looking at the behavior to the right and to the left of it, we were able to show that it is in fact a global minimum. And that's all that we have for today. Again, thank you for tuning in and for bearing with the technical difficulty in the first little bit. Again, like Mr. Maple has mentioned, we have office hours, which is on Thursday from 1 to 3. So feel free to step by. It's through Big Blue Button on Moodle. If you also have questions, email is always a good way to ask. I can always jot something down on paper to send it to you. And we'll pick up some more interesting business administration and economics applications on Thursday. Again, I'd just like to repeat that we have posted a assignment, and we'll be working through more of that material tomorrow, or on Thursday. Yes, and the test, I hope to have it done by Thursday. I hope that answers everyone's questions. Hopefully it wasn't too, hopefully it was straightforward. Excellent. Thanks again for everyone tuning in. Have a good night.